Hey Trick Class, this is your notes for 9.1, application involving right triangles. We've seen a lot of this already. It's like right triangle trigonometry, but we're going to get into some application as well as just the generic theoretical stuff with right triangles. Alright, obviously the right triangle, the Pythagorean theorem applies to the side lengths, and the 180 rule applies to all three angles. Therefore, because it's right, the two acute angles will always be complementary, meaning that they add to 90 degrees. Right, there is an error here on this slide. That's supposed to be 35 degrees. I don't know why it says 40. So that should say 35 degrees. All right, now given that, because the angles are complementary, and that one again opposite the little a is side big A, that means that has to be 55 degrees because 90 minus 55 is 35. So that's our two angle measures. And now we're going to use trig to find the two missing side lengths. Notice that side A that we don't know is opposite this angle 35 that we were given. Typically use the given ones. That way, because you know that they're right. If you made a little arithmetic error on this, then the other angles would be, the other side lengths would be wrong if you use this angle. So if you use the side that you're given, it should be a better starting point than to use the ones you have to derive yourself, especially if you had to round them. But anyway, let's go through and let's find side A. That's opposite the 35 degrees. 4 is adjacent that 35 degree angle, so that means we could use the tangent function to come up with side A. We could also use the cosine function, because this is the adjacent side, this is the hypotenuse, and we could set up cosine is adjacent over hypotenuse, so 4 over c, and then we could do a little bit of arithmetic to solve for those. So A is approximately 2.8, and then c, that's 4 divided by the cosine of 35, which we could also write, I should say, 4 times the secant of 35 degrees. That would also give you that. Either way is fine. You just type it in your calculator, and you would do 4 divided by cosine 35 on a TI calculator anyway. Alright, for this next example, we've got two side lengths. We don't know the third side length, and we only know the 90 degree angle for the three angles. So because we're given the two legs of the right triangle and not the longest side, we can use the Pythagorean theorem to come up with that hypotenuse. So c squared equals 4 squared plus 2 squared. That's 20, the square root of 20, and then simplify. Right, 20 is 4 times 5, right? 4 is a perfect square. That's why we're doing that. The square root of 4 is 2. So we pull that out, leave the 5. Or we could approximate about 4.47. 2 square root of 5 is the exact value. So you would expect it to do that for a lot of application. But if it tells you to round, make sure you read that and round. All right, for angle A, I can do opposite is 4, adjacent is this side that forms the angle with the hypotenuse is 2. So the tangent of angle A is opposite over adjacent, 4 over 2. So I can find A with the inverse tangent. Inverse tangent of 2 is about 63.4 degrees. All right, and then because now I know that that's 63.4 degrees, I could set up another trig function, but again, A plus B has to be 90. So I can just get this one from 90 minus 63.4. And that's where this 26.6 is coming from. All right, next we just get into the same type of thing, but it's in an application. So we're going to have these pictures that have these right angles, okay? If the right angle wasn't there, if this picture wasn't there, you would need to be able to kind of sketch a picture yourself. All right, so we got a starting point of 8,000 feet. We're increasing up to this 11,100 feet. In elevation. So that's like the new height that we're going to get to. So that means that this change is the change in height. It's the 11, it's that change in elevation is what we're doing. So we're just subtracting to get that change. That's that part of the right triangle. And then it tells us the trail length, which is the hypotenuse. It's connecting the 2 points, is that 14,100 feet. So we basically have the hypotenuse and the side opposite the angle that we're trying to find. So because we have the opposite and the hypotenuse, that's the sine function. Right? So we set up sine equals that opposite side length at 3,100 divided by the hypotenuse. Inverse sine then is what we need to unlock angle B. So inverse sine to the 3,100 over 14,100 is about 12.7 degrees of elevation. So you've probably seen grade, like when you're going down the road and you're going down a steep hill, if you're coming out of the mountains, and that's what we use to measure that, just the change in elevation over the distance. All right, on this example, we got a little bit going on that you would need to kind of know ahead of time. So one is the radius of the Earth. So this is the radius of the Earth from the center of the Earth. This also is the radius of the Earth to a different point on the Earth. It's just this point they've added the lighthouse. So it's 100 feet on a hill, right? And there's a hill and then this lighthouse. So altogether, those things add up to 400 feet above the surface of the Earth. So this is greatly exaggerated because these are miles, and we can actually see this when it's only 400 feet. So before we can proceed, and this is a right triangle, this is the hypotenuse of that right triangle, but these units don't match. So we're going to convert this to miles so we can add that little difference in miles, and then we have an adjacent side and a hypotenuse. So the very first thing we do is set up our trig function. So this is adjacent, this with the lighthouse included is the hypotenuse, so that's going to be the cosine of this central angle. So the cosine of the central angle is the adjacent side, the 3960, and then we divide that by the 3960, but plus this tiny little fraction of a mile. All right, a mile is 5,280 feet. So this 400 feet is just a fraction of another mile. Now, once we have that central angle, it's the inverse cosine of all that, we'll know what this angle is, and if we know what that angle is and this distance, right, then we can solve for that arc length. And that arc length is the distance that they're claiming that they can see it on the horizon. It's the distance from the lighthouse over here to that other point on the Earth. Okay, that's what ultimately our goal is here. All right, so when we do this division, this value right here is so tiny. 500 over 5,000 would be a tenth. So it's not even a tenth that we're adding. It's 3960 on the top and basically like 3960.08 or something on the bottom. And it's almost one. It's almost the exact same thing. So the cosine of the angle is virtually 1. So the angle is very small. It's a tiny little angle, not even a half of a degree. So if we convert that to minutes, because it's not even a whole degree, we get about 21.26 minutes. And this is another thing that you would need to kind of know up front. Nautical miles. So nautical miles is that measure of the angle in minutes. So the 21.26 21.26 minutes is how many nautical miles that distance is. So S, this distance that I was mentioning that we're solving for, that's the distance along the Earth. If we use the angle in minutes, is 21.26 nautical miles. Now the other way we could do it is arc length. So if the radius, again, is that 3,960 miles, and we have a tiny little, not even a half of a degree, we could find that arc length, the distance along the Earth, if we convert that angle to radians. So that 0.3544 degrees is not even a whole hundredth of a radian, but we can convert that into radians, multiply that by that central angle, that radius, and that gives us 24.5 miles. So either way, if we're using the arc length formula, if we're using the nautical miles from the minutes, it's not what they say. Remember, they claim at the very beginning it's about 26 miles that it could be seen, and the longest of these two that we're seeing is 24.5 miles. So it seems that they're kind of overestimating the distance. All right, another big application for just trigonometry in general is bearings. So bearings are typically measured with degree measures, but we start off from north and south. So we start north and then we say north 30 degrees east, south 20 degrees east, south 50 degrees west, etc. It's north-south first, then we measure our angles off the north-south line. Now it's a little bit different than what we've been doing standard position in trigonometry all semester. We start off on that positive x-axis, which is the east line here. So it's a little bit different than that, but north and south are our original kind of point of reference, what we're basing the angle off of. So 4 is going to be south 20 degrees east. Alright, so when we're doing bearings, again, typically those are transmitting back and forth between some type of tower, like if it's at an airport or if it's in a boat in the ocean, they tell their position with these bearings. So this is the initial bearing that we're on, north 20 degrees east. So there's north, go 20 degrees off of that east, and that's where that plane is flying. So it's done this for a mile. The pilot requests permission to turn 90 degrees and head towards the northwest. Okay, so 90 degrees would be in that direction. And then it goes 2 miles in that direction. So now we want to know what should the new bearing be. So we'll see on the next page, but the key to unlock this is we've gone 1 unit in this direction, and then we turned 90 degrees, went 2 units in this direction. So if I connected that initial point with a straight line, I'd have this angle, right? And it said we went 90 degrees, so that's 90. And so I have a right triangle, and this is the side opposite the angle. This is the adjacent. So I'm going to be able to set up the tangent function to start this process off. So I could use tangent, inverse tangent to solve for the original angle, or the angle that's swept out from the original trajectory to the end of the new one. But I'm going to have to eventually subtract away this 20 degrees. So that's the process here. I'm going to get that 63 degree angle, that's all of this. But because this one is 20, I can take that 20 away and have a 43.4 degree off of north. And remember, that's how we do it. It's north or south first, and then how many degrees off of north or south in what direction. So that means we have north 43.4 degrees west is our new bearing that we're on. Alright, so this is, again, this should not be completely brand new. This is a lot of application of right triangles, and we've seen a little bit before in the right triangle trig section.